Okay. Okay. So let me start by thanking Eric, José, and Vitor for putting this together, and I'm very grateful for it. And I'm not going to say I'm grateful for inviting me because I think it's sort of obvious. But anyway, thank you very much. Today I'm going to talk about work that I've been doing with my old-time collaborator, you guys may know, Vlado Brosavljevic. This is work done with one of his students, Tsung-Han Lee, my student, Martha Villagrán, and in collaboration with Darko Tanaskovic and Yaksha Vucicevic. Thank you. That took a while. So I'm going to talk about strong correlations and inhomogeneities with a little bit of goodwill. You might say there is frustration. There's absolutely no topology. Okay, so let's start with the Mott transition that Vlad and other people talked about a little bit in this conference. So there are a few scenarios that about our view of the Mott transition. Let me start with this possibility of it being a purely second-order transition, even at t equal to 0. This is probably important in 2D, where you don't expect magnetic order on either side. And there is some proposal for this transition being a second-order transition at t equal to 0. And there's recent work in Moiré superlattices and TMDs that seem to support this view. But I think generically, we can say that it's usually a first-order transition at 0 temperature with the first-order line ending at a second-order critical point at finite temperature. And of course, at lower temperatures, there are several instabilities that might occur, and they compete with each other, and things may be complicated. But the physics up there is rather simple, is this the first-order line ending at a second-order point. Okay, so for instance, these are some examples. I think some of these were shown here of organic materials where you do see this first-order line ending at a critical point. There's interesting physics up here. I may mention them in passing, but for now, just focus on this first-order line ending at the critical point at finite temperature. So if you look at a phase diagram of a liquid, of a normal solid liquid gas material, in a PT phase diagram, you do see, of course, a first-order line ending at the critical point, separating the gas phase from the liquid phase. And this is very similar to the picture of the Mott transition I showed before. So here's an example of another compound, sort of paradigmatic compound, vanadium 2 oxygen 3 doped with chromium, where you have this first-order line. There's a coexistence region ending at a second-order point. Anyway, so just like in the gas-liquid transition, where you can go continuously over the second-order point from the liquid to the gas, here also, I think there's something wrong. You have a very similar scenario. You can actually go continuously from the Fermi liquid, the metal, to the Mott insulator if you go over that line, and you can do so continuously. Because at finite temperatures, you cannot actually distinguish a metal from an insulator. That can only be done at 0 temperatures, just like that. And so, of course, over the years, this transition has been studied, and as expected, it has a character that is very similar to the liquid-gas transition. It's, for instance, if you look at the conductivity behavior, you see close to the critical point some critical exponents that can be measured, and they look very much like the critical exponents of the liquid-gas transition, which is in the IC universality class. It's actually very close to the mean field values of those exponents if you're not too close to the critical point. At the critical point, you see corrections, and you recover non-trivial Ising, 3D Ising exponents close to the transition. This is what this paper is all about. And so the collection of these data is compatible with a transition that has a scalar order parameter, just like in the Ising model or in the liquid gas case. Here you go again. Yeah. Anyway, there's, I have to touch it here. I don't know what to do. No, I have to get out. All yours. Okay, okay, good. Yeah, that's the problem. No, it's okay. It's working, I think. No, it's not working. No, wait. There. Yeah. It would be nice if this didn't happen again. All right, thank you. And of course, as you probably know, there is a good description of this behavior. Oh my God. Using the dynamical mean field theory. Now click play. No, but you have to touch. It doesn't work. Okay. Okay. All right. Here we go again. So this transition has been, especially at high temperatures, well described by this theory, this approach called dynamical mean field theory. So, for instance, if you use the Hubbard model for the description, the dynamical mean field theory, which I'm going to summarize now, is basically a description that assumes that the electron self-energy is local. It doesn't have any K dependence. And it can be justified in infinite dimensional limit. But of course, we are in finite dimensions. This is just an approximation. And the spirit of the approximation is you solve an impurity problem in the bath of the other electrons. So you focus your attention on one of the sites of the system. Electrons can go in and out of that site. The site is correlated. So you solve that impurity problem, and then you impose self-consistency, assuming that that site is no different from the other sites, and you have the theory. Of course, the difficult part is to solve that impurity problem, and there are several approaches that can be used for that, but that's the idea. So from that, you can get a very good description of that transition, first-order line ending at the critical point that's been done over the years. Now, what I want to talk about is the effects of inhomogeneities when you introduce, for instance, disorder in a system like that. What happens? So let me show you some pictures of, for instance, the other important compound, VO2, that has a metal insulator transition. And this is scanning infrared microscopy, near-field infrared microscopy, that has a reasonably good spatial resolution. And you can essentially measure the local conductivity of the sample. And as you go through the transition, you see the formation of these puddles of metal and insulator. So for instance, here, the blue line is low conductivity. The red and green line is larger conductivity, so you can say you have domains of Mott insulator coexisting in the transition region with domains of a correlated metal. This has been seen in V203 as well, with the same technique. So you see these puddles forming. This is higher resolution than here. And as you go across the transition, as you cycle across the transition, like so, you see the formation of these puddles. Of course, when you furrow into in the metal, you have a more homogeneous situation. Same thing in the insulator. But as you cross the transition, you have this formation of these inhomogeneous patterns in your sample. These are fairly large puddles. The length scale there is given by that bar, which is 1 micron. Okay, so what I want to talk about is the physics of those inhomogeneities. Okay, so of course, the first thing you think of doing is to introduce disorder in the Hubbard model. Okay, so you can put a site disorder term in the Hubbard model, distributed somehow. It could be a uniform distribution. It could be bimodal distribution. It doesn't matter too much. And then you want to solve this problem. So what we have been doing over the years is to use sort of an extension of dynamical mean field theory that takes into account spatial fluctuations of the self-energy. So the self-energy, which before was the same all over the sample and dependent on frequency, now it varies from site to site. And just like before, you have to solve an impurity model for each site. Now, of course, each site is going to be described by a different impurity model than the other sites. So the complexity of the problem increases considerably. And you have to impose self-consistency, just like before. So that's the idea. So we assume local, but spatially fluctuating self-energies for the electrons. And we impose self-consistency, in the sense that this site will see the rest of the lattice summed over, and will also feel the spatial fluctuations of the other sites. Note that, for instance, the way we do it, of course, it's a much more complicated problem now, but if you turn off interactions, this approach is essentially exact. So you have, for instance, a localization transition. You have everything that a disordered fermionic problem would have. At zero disorder, you recover dynamical mean field theory, the homogeneous dynamical mean field theory I mentioned before. But of course, we're interested in the problem where both are there at the same time. And once again, the hard part is solving the impurity problem. Now, the number of impurity problems has increased a lot, and the problem becomes very hard computationally. So the first work that we did, we used quantum Monte Carlo to solve the impurity problem. And you can see here sort of the spatial profile of this. This is a two-dimensional model. And the quantum Monte Carlo is solved on the imaginary axis. So the easiest way to characterize the behavior as being metallic or insulating is to look at the imaginary part of the Green's function. Unfortunately, what we can do here is to look at the first Matsubaru frequency. That's not ideal, although that does have the expected behavior in the sense that this should be finite in the metallic regions and go to zero in the insulating regions. And that's what you see here. The color scale is here. As you cross the transition, as you crank up U here at fixed temperature, you do see the formation of those same puddles that I showed before. And eventually, you're completely insulating over on this side and more metallic on that side. I call your attention to the green areas. Actually, it's shown here also. This is as you increase the system size for fixed U. And of course, if you could increase this further, you would see the same kind of Imuri-Ma phenomena of the main wall formation. And you see sort of the beginning of that Thomas talked about. So the thing to be looked at here is that the metal and which is the red part, and the insulator, which is the blue part, they're separated by these green domain walls, and they're not small. They're fairly large, even compared to the size of the puddles. So the question we asked ourselves, okay, so this is what I said, but the question we asked ourselves is, what is the nature of the fermionic problem when you are deep inside the domain wall? We know what to expect from the Mott insulator, roughly at least. We know what to expect in the metallic regions. The question is, what happens in the domain wall? Since they are so large, they're surely going to play a major part in the physics of the problem. So this is the question we posed ourselves. So the first thing we did was to sort of zoom in on one of these domain walls, and you can define on the side a one-dimensional problem, sort of mimicking this narrow region here as you cross one domain wall. And what you can do is that you can fix one side of a long one-dimensional chain on the metallic solution, you fix the other one on the insulating solution, and you look at the behavior in between as you go smoothly from the metal to the insulator. So you basically, this is equivalent to taking an Ising model, fixing the magnetization as being up on one side, down on the other side, and look at the domain wall. Okay? So this was done with iterated perturbation, second-order self-consistent perturbation theory, and analytically continued to the real frequencies, frequency axis with the approximation. So, so this is the phase diagram of the model, of the clean model. This is the first order line, the green line here. You have the yellow, the red line is the spinodal line where the metallic solution becomes unstable. The black line is the reverse, where the insulating solution becomes unstable. And within this triangular here, both solutions coexist. Of course, they have the same free energy only along the green line, but they are local minima of the free energy inside this triangle. So you can fix, as I said, insulating behavior on one side, metallic behavior on the other side, and look at what happens in the middle. So first thing you should look at is the behavior of the width of the domain wall. Okay, as you go along this first order line here, so it's the green arrow over there, and you can see that, for instance, as you approach the critical point, which is this, what's it? It's a pink line. The width of the domain wall becomes very large, and that's absolutely to be expected. The correlation length is diverging as you approach the critical point. This should be very large. So this is the inverse of the domain wall size. As you approach the critical point, this should go to 0. The domain wall size is diverging. Interestingly, it goes to 0 also on this side. This is because within this theory, this point is also a second-order point. I'm not going to go into that, but this is why this happens here. Okay? So you see that basically because of critical behavior, the domain wall sizes are very large close to the transition. This is totally to be expected in this case. Now, so what we want to look at is the fermiology, the fermionic behavior in each of those regions. So we can look at the scattering rate, so the imaginary part of the local self-energy. For instance, you can look at it here at the center of the wall, deep inside the metal or deep inside the insulator. And what you see is over here, so of course, you expect that in the metal, it should go down. In the Fermi liquid-like behavior, like T squared, it blows up exponentially in the insulator. And at the center of the domain wall, it doesn't know where to go. It stays roughly in the middle, okay? So this is very, in terms of fermions, this is very strange, because a self-energy that's going to a constant as you decrease the temperature. And it's sort of flat as a function of the temperature. So this is already something, but we wanted to go a little bit further and analyze this in more detail. And so let me remind you of the Landau functional description, once again, this is a mean field treatment of the problem. So let's first look at what the mean field behavior is for the Ising model. That's sort of behind this treatment. So this is the Landau functional appropriate for an Ising model close to the critical point. Okay, so you can try to solve the domain wall profile close to the critical point, and this can be done actually analytically. And as you expect, it has this Tench behavior here. The width of the wall is governed by the correlation length. And of course, what's going on here is that you're going from, let's say, an up magnetization to a down magnetization. You're going from one minimum of the Landau functional to the other one. But to do that, you have to go over the line, the mountain, in between. So you have to pass through the maximum of the Landau functional to interpolate between one side to the other, okay? So this is just saying what I just said. The center of the domain wall corresponds to the maximum of the Landau functional, okay? Which is, in a sense, not, it's an inflection point of the Landau potential, but it's not a minimum, it's a maximum. And of course, you expect the same kind of behavior for the metal insulator transition because it's the same kind of order parameter and there is universality, you expect the same thing to happen. So if you go, as in the description I was showing before, if you go from the metal on one side to the insulator on the other side, you have to pass through the maximum of the Landau functional, and that should be at the center of the domain wall. The question is, can we focus on this point here, try to describe more precisely what's going on there, and learn a little bit about the fermionic behavior in that region? So that's what I'm going to show you in the last few slides. So the Landau functional description of dynamical mean field theory has been done also. You have a free energy, which is a function of the order parameter, which in our case is a function of the frequency. Let's say, for instance, in terms of the Green's function, it could be the self-energy, it's equivalent, but here written in terms of the Green's function. So this is the Landau function that should show that kind of behavior that I showed you before. And one of the things you can, if you want to find the solution at the maximum of the functional, that's very hard because, you know, numerically, usually you're driven to the minima of the functional if you don't do anything. So what can be done is the following. First of all, you can find a sort of an approximate solution to the problem by smoothly interpolating between the stable solutions on the metallic side and insulating side like this. Oops, sorry. Okay, like this. And then you can use the functional form here to go, if you start, for instance, from the metal, you can calculate the variation of the functional, of the free energy as you cross from one side to the other by varying this L parameter here. This can be done. It's not very difficult. And you can find the variation of free energy as you go from the metal to the insulator. And this is what's shown here. And as expected, there is this two minima structure separated by a maximum. And as you go through the transition, of course, one minimum, for instance, this is the stable solution here. It goes up, it becomes the global minimum at some point here. Of course, it is the global minimum, but then the global minimum becomes the insulating one. And you can follow this. You can construct this Landau functional the way I showed you before. And of course, I want to focus on the maximum. Okay, so you can find the convenient L there for that maximum, and use that as a first approximation to the Green's function at the maximum. But of course, this is not the full solution to the problem. What you actually have to do is to, starting from that good initial guess, use some sort of numerical method to converge to a maximum of the functional. And this is what we have been able to do. We use this method, Broyden's method, to try to, starting from this initial guess, converge to the maximum of the Landau functional. And what I'm going to show you is the behavior of that solution, the maximum point solution. Once again, in this case, actually across, along the green line. So fixing U and just decreasing the temperature and going through the transition. Okay? Also, once you have the solution, you have the self-energy. And with the help of the self-energy, you can calculate what a conductivity of a homogeneous system would be if it was completely homogeneous and was in that state which we call domain wall matter. Okay? So in other words, if you would be able to put leads on a very large domain wall from one side to the other side and measure the conductivity, that's the conductivity you could measure, you should measure. Okay? So this is just the standard formula from using the self-energy to get the conductivity within dynamical mean field theory. As a reference, I use here the conductivity at the so-called Mott-Joffe regular limit, where the mean free path is on the order of the lattice parameter. So here I show, for instance, with two techniques for solving the impurity problem, iterated perturbation theory that I was showing before, and quantum Monte Carlo, continuous time quantum Monte Carlo, and the three solutions, the metallic solution, the insulating solution, and the domain wall in green are shown here. And here's the resistivity scaled by the Mott-Joffe regular limit. Okay, so of course, in the metal, you expect Fermi liquid behavior, T-squared behavior, exponential behavior in the insulator, and the domain wall, as you can see here, is uncertain where it should go, and it goes in between. Okay? And with IPT, you see similar behavior, not very different. Of course, this is more accurate in terms of solving the impurity problem, but also much more difficult. But you see that the behavior is very similar. So as I said, the metallic solution is conventional Fermi liquid. The insulated solution also Mott insulating behavior. And the domain wall is strange. It's a strange metal, or what is it? Okay, so you have, for instance, if you look at the value, the numerical value of the resistivity, it is going above the Mott-Joffe regular limit. Okay? But it's not an insulator, so what is it? Okay? I'm not sure I'm going to be able to answer that question. I'm just going to show you what the behavior is. As I said, we can say at this point that the domain wall matter is a bad metal, perhaps a non-Fermi liquid, or something else. So can we look a little bit closer at this behavior? So here I show the imaginary part of the Loga-Green's function for the three solutions, but just focus on the, well, let's look at the metallic solution. Has that behavior that was shown here before, two Hubbard peaks and a quasi-particle peak in the middle. And surprisingly, the domain wall also has a quasi-particle peak. Okay? Of course, in the insulator, you open a Hubbard gap, but what we see here is that the domain wall matter does have a quasi-particle peak. In both cases here, this is different temperatures. You see a small but clear quasi-particle picture in the middle. So a quasi-particle picture suggests that you can describe this behavior in the usual way you describe a quasi-particle. For instance, the Loga-Green's function of a quasi-particle is characterized essentially by two parameters: the quasi-particle weight, Z, okay, which is easily obtained from the self-energy, and from the imaginary part of the self-energy, you can get the scattering rate. Okay, so you can essentially parameterize the peak with these two parameters and look at the behavior of those parameters as a function of temperature as you decrease the temperature across the transition. So this is what we see. For the metal, the Z goes to a constant. This is a conventional metal. The scattering rate follows a t-squared law, as in a Fermi liquid. But now we look at the domain wall. Okay, so Z is plummeting to 0 as a function of temperature. So it is finite at a finite temperature, but it's going to 0 very fast, actually, as t-squared. And, okay, this is the metallic solution. And the quasi-particle rate is going up with decreasing temperature, with t-squared. Okay, this is absolutely not what you would expect from a metal, although it does look like it allows for a quasi-particle description. Okay, so it's a strange quasi-particle that's seen here. And this is reminiscent to previous work that characterized the Hubbard model in the metallic region as a function of temperature, and this was called in those papers a resilient quasi-particle description. Certainly not the behavior you would expect in a Fermi liquid, but I remind you that in this study here, the behavior is not as dramatic as seen here, where Z goes to 0 and gamma diverges as a function of temperature. So, so that's it. I think I'm early a little bit, but that's okay. So the conclusions are that it pays to look at the inhomogeneous Mott state, and especially at the domain walls. They are there. They seem to be large, and they are certainly going to play a role in the overall conductivity behavior of the system. And what I tried to convince you is that the domain wall behavior, the system doesn't know whether it's a Mott insulator or a metal, and in that undecided state, it behaves as a bad metal and a non-Fermi liquid. And of course, as future directions, of course, we haven't done that, but we would like to be able to measure the full transport of the system, where we have metallic puddles, insulating puddles, and domain wall matter in between. Okay? So that's for the future, and with that, thank you very much.
So thank you, Eduardo. Questions? Oh, I see.
Eduardo, when
Yes.
you know, one of the things of the Mott transition, not in VO2 that you have an actual change in the structure, but most of the other cases is there's a volume change.
Yes.
So there's this coupling with the strain, with the acoustic phonons, which cause these long-range interactions and the mean field behavior and whatnot. That's at least the usual story.
Not
so,
necessarily, but okay, anyway. Go ahead.
So, I mean, there is the long-range interaction. And, okay, we can discuss whether it's mean field or not, but...
Whether it's relevant or not, but
right,
anyway.
but
okay.
wouldn't you expect that for the domain walls is going to be important? Because there will be elastic costs, and because the elastic the strain goes as, you know, is not exponentially decaying. Would this be important in any way here, or? I mean, it's a hard question, but I just see if you have any feelings for what. If this could be handled somehow.
Perhaps, I don't know. But I think the behavior close to the critical point, I think you were one of the people who showed this, is pretty compatible with the dynamical mean field theory. Absolutely, yeah. And
blame it on the strength.
Not necessarily. I'm not sure I agree with that. You certainly didn't need to use the strain to explain the conductivity behavior. So to me, that is a sort of a experimental proof that it's not relevant to the behavior close to the critical point.
I have a somewhat simpler question. So what dictates the width of the domain wall in your calculations?
It's just, well, it's a correlation length of the transition, right?
Is this can this be influenced by anything, or is it Is it in some sense God-given? So, I mean, you showed your numerical results, and there were wide domain walls. You could ask, is it God-given that they are so wide, or can they be even wider in the material, or something like that?
Well, the clean system is given by the correlation length, and that's roughly what was shown somewhere here. So let's see if I can find. Oh, this one here. This is essentially the clean system behavior, because we are fixing the phases on either side and looking at the. So in a sense, if you look at this interface here, this is just an interface between an insulator and going to the metal. And so you'd expect that is governed by the correlation length of the transition. It is. And as I said, the reason why it goes to zero, the inverse goes to zero, is because it's also a second-order transition within this treatment. Okay, so now if you put interactions, there's going to be some interplay. There's going to be, but if, for instance, perturbatively, if you put impurities, if you put impurities, there's going to be some interplay. But if you think of it perturbatively, what you're essentially doing is just creating the domain wall with impurities, right? And perturbatively, you expect the domain wall to be governed by the correlation length. That's what we see here. It's completely compatible with that.
Yeah, thanks. I actually just wanted to add something to what Raphael said, because in the kappa organics, we actually measured exactly what Raphael was pointing to. So we had measured the lattice effects across the Mott transition and have shown that it's, well, first of all, that the lattice softens enormously across the Mott transition, and that we need sort of, that if we describe the lattice effects, that we get mean field behavior because of this coupling to the lattice. So I think I'm just sort of, I was having the same question as Raphael.
Where do you focus your study? I mean, in terms of the first order line?
Close, around the second order critical endpoint.
Okay.
I mean, I'm happy to show that to you later.
Sure.
But we've seen that to temperatures much higher than the critical endpoint, these very strong lattice softening. So if there's any way to include that in the theory, this would of course be very, very exciting.
I think it can be done.
Two quick questions. One, the inhomogeneity in the experiment. If they anneal the sample and cool down again, would they see the same pattern, or do the pattern changes? In other words, is this inhomogeneity some kind of frozen fluctuation, or there is intrinsically impurity that pin those fluctuations?
Good question. Yeah, I think the answer is in the paper. I don't think it comes back to the same. But I'm not sure, to be honest. This is cycling across the transition. You know, this can be, your question can be answered by looking at the data here.
Okay.
And I'm sure in the paper, there is the answer there.
It doesn't look like it's repeating, right?
Well, it doesn't go twice, right?
All right, so that's my first question.
It does, actually.
Yeah,
okay.
but of course,
Yeah.
In absence of disorder, there will be only two states, one stable, one metastable. In reality, when you put disorder, as everyone knows, there are many local minima, many metastable states, and the hysteresis loop explores, exploring many of these metastable states. And as a result of this, there is also some slow dynamics associated with any hysteresis behavior. And in fact, in these Mott organics, there is a Japanese group that has actually explored the time dependence of some of these domains, and they do show the expected behavior. So, these are metastable states. So in that sense, yes. I mean, if you cycle it thermally or in any other way, you'll explore many metastable states.
right. And so in that sense, I can understand the numerical study here as a way to use external disorder to pin some of this fluctuation, right?
Yeah.
But in essence, if you don't introduce this disorder, this kind of physics will happen. It's just harder to study because they will come back and forth, and your study will be very difficult to analyze, right? Yeah, all right. Second quick question is, what about you show the temperature independence of the scattering rate?
Yes.
Up to the point that you stopped. And it seems it's constant, right? I'm
Seems
just curious,
yeah.
if you keep going to a higher temperature, is it going to be constant all the way, or at some point there will be some additional
they merge,
dependence?
right?
I'm sorry?
They merge. You're going to higher temperature?
Yeah, higher temperature.
They merge.
there is this is the one, right? Yeah, and if you keep going higher than that, what happened? The scattering rate above that.
Well, it's like
second order
going
point.
over the critical point.
Yeah, what happened after that?
It's like if you're above the liquid-gas transition, is it a liquid or is it a gas? It's neither or both.
I know. I'm just asking the scattering rate. How
Well,
is this
they
rate going to
merge,
change?
and I don't know. Yeah, probably.
You know, you see all the resistivity curves, they bifurcate at low temperature and high temperature, they all merge, right? And they're basically molecules of regular liquid. This is true in all metal transitions.
You won't. I guess you're still far away from the bandwidth scale, right?
From
Because at some point it will become classical, and it should have some T-linear dependence. Okay, all right. Thank you.
So Thomas, please.
Could you go back to the picture with the domain walls? I have a follow-up question to Matthias' question.
The experimental one?
Yeah, this one is
Okay, okay.
So he asked about the width of the green regions, right? But the red domains, they seem to be much smaller. So that's unusual to begin with, right? And then also, what sets the scale of those?
The red domains?
Should there only be one length scale is the problem? At least according to the simple picture that you painted. But these red blobs, they are certainly smaller than the domain walls, right? Or at least.
No, not really. I think they're set by the fluctuations of the disorder. It's like a random field.
So you think it's the same scale?
Yes. Well, let me show you here.
Imri, in my picture, right, the domains can be much bigger than the correlation lengths, but whereas the wall width, of course, is the correlation length.
Yes.
But there should be some very large domains.
Well, if you depends on the side where you're on, right? They certainly grow on the other side, right? They grow smoothly across the transition. But they are certainly determined by the fluctuations of the disorder. We actually tried to do this more quantitatively. And it does correlate, for instance, the variance of the disorder fluctuations in the respective regions. There's a very clear correlation there.
Still, the fact that this kind of looks opposite of what we normally draw a domain pattern, right? Which would have large domains with finite widths, but comparatively to the domains as narrow domains. Here looks the other way around. Makes me wonder whether something else is going on in addition to just domains.
Yeah, I think, as I said, I mean, everything we did, it was completely compatible with a random field Ising model behavior, even quantitatively. I didn't show it here, but it's in the paper. You can do this characterization. Now, maybe we have missed some steps. Of course, the sizes are small, right? I mean, this is the most we can go. This is a lot of work. This is 400 impurity models being solved at the same time and self-consistently determined for different temperatures and use.
So unfortunately, we have to move on. Okay. So let's thank Eduardo again for this nice talk.